invite today. I look forward to talking to you, and we're going to talk a little bit about the brain and biomechanics today. So there's my disclosures, and this kind of journey started in the 1990s when our orthopedic surgeons started to realize they were having a large proportion of female athletes come into their clinic, and they said, well, what's this problem? And so to get after this problem, we had to say, what's different about boys and girls? So the first thing we naturally looked at is females tend to have different anatomy, hormones, and some neuromuscular control, but we focused on that a little bit. These are non-modifiable risk factors and things that we didn't really find were driving the risk. And what it came down to is these factors probably have some effect on it, but what we were looking at the biomechanics and the mechanism of injury, it was ultimately coming down to that knee load. And so this is a good thing, because if it's a knee load and it's neuromuscular in nature, that means that we can target and train against this. And so this is kind of when it hit me. I said, can we start to do neuromuscular training to start to prevent injury and move the field forward? And so our first soiree at this is we looked at this at a preseason strength conditioning protocol. You can see we probably weren't correcting the mechanics very well, but we did get a bump in injury prevention. This kind of set the baseline for what we could get with a traditional strength conditioning program. But what we did is we went back and looked at what exercises to include in a traditional program. And what we found is some exercise, balance training was a craze back in this day, and people were doing a lot of balance training. We found that balance training actually increased the risk of it. And do we think balance training is bad? No, but what that meant is they weren't doing enough of the real exercises that matter, the landing stabilization, core, and core training. So we took this information, designed a really reactive trunk and core training program to see if we could improve the injury risk reduction. And we took that program and we got a nice little bump in injury risk reduction doing this a more advanced training protocol. The next phase, what we wanted to look at is what's causing these young girls to have this ACL injury, what's the mechanics, and what we were able to identify is several biomechanics that was highly predictive of an athlete that was going to go on to this type of injury. So we started to design training programs that were built upon targeting these high-risk biomechanics and risk factors, and we got another nice bump when we started to target these risk factors for injury. And so by this time, this is around 2008, we were showing that if you implement these injury prevention programs, we were getting a 50% reduction in ACL injuries in female athletes. And by 2008, these programs were showing consistent effects of reducing injury. But you look at some of Jen Hagel and Jen Hoopman's data, they're still seeing an increase in ACL injury rates among females, and that disproportionate rate among females to males. And so we hadn't solved the problem. So again, went back to the drawing board and we started to look at, well, some of these programs weren't using ideal biofeedback. You see the circled ones. They weren't doing training the way we thought you should. It also mattered who was implementing the training. Did they have some experience in implementing it and having some expertise in driving that? And so we're at this stage now. How do we take some of these risk factors we've learned in these biomechanics lab? We've informed the training. We know what the problem is. We know how to fix it. How do we translate this into training programs that can actually solve the problem, really taking advantage of the key feedback and training of principles for athletes? And the other idea, and Kritika has showed this, is that biomechanics relating to ACL injury are not a single factor. It's not just about the knee. You can see this athlete, we're lucky they didn't tear their ACL during testing. There's a multivariable risk factors for ACL injury that we have to target. So our next approach for this was to develop a program or a technology we called augmented neuromuscular training, or ANIMATE for short. And the idea was this was going to be a multivariable biofeedback system where we would have individual risk factors that would disrupt a single stimulus to them. So when they would have bad mechanics, they would disrupt the square in a specific way. And then we took all these risk factors and had them scaled to a similar scale, and then we fused them to work all at once. So an athlete would be given multivariable feedback that would guide their movement, and then we set up a gain control where we could target specific risk factors, turning up and down the gain as we went. And so our solution is we called ANIMATE. We developed this multi-dimensional self-guided biofeedback system that could help correct movement mechanics for athletes. And so you see here, we did this training program with a group of athletes, and we got another nice little bump with our injury risk reduction. But if you guys are starting to see that my plot, we're starting to hit diminishing returns. And this is what I meant Dustin Grooms, and he's told me, he goes, "You're an idiot, Greg." He says, "You're doing all this biomechanics. It's actually the brain and the central nervous system." I didn't know the brain was even connected to the biomechanics. So he told me that he said there's a sensory motor error during these ACL injuries. And so our first attempt at this is we started doing prospective resting state. And resting state means you're laying in an MRI, not moving. We found some sensory motor connectivity issues in those athletes that would go on to an ACL injury. But I think we need to have movement whenever we could look at movement biomechanics. And so we developed a biomechanics system inside the MRI. We started to look at those athletes on how their brain was controlling their motor control. And we found those athletes that were worse movers, they were more likely to have a lot of reduced sensory motor, and a lot of cognitive. So they were thinking about how to move. And then we increased the task complexity, and they started to try to visualize. They were trying to use their senses to do this simple task. And so we developed a system where we integrated a biomechanics system into the MRI, and this further showed that those athletes that were poor movers, they were trying to think and visualize movement as opposed to being more automatic. And so the idea is, can we start to take this sensory motor response and can we start to optimize biofeedback? And so we tested athletes in a virtual reality scenario competing against avatars and then measured how their brain performed before and after training. And we found that those athletes that improved their biomechanics, they had a better sensory motor integration, or they became more neurally efficient, so they had more resources available to perform those biomechanical tasks. And we do think that we can start to do that. So my point in leaving you with today, I want you to start thinking differently. Can we train with the brain to start taking that last bit of injury risk reduction we need for female athletes, and that'll take us to where we need to go for the future. Thank you.